Alrighty, I got a couple of work energy problems here for you. The first one is about a bullet. They give the mass. They say its initial speed and it strikes the hand of some superhero, and they tell you how far the superhero's hand has moved. And then he stops the bullet. And they want to know what's the average force that stops the bullet. Okay. And then they say, assuming the force is constant, determine how much time elapses. Okay. So this is classic work kinetic energy. Let's just write what that means. Work equals delta KE. Okay. So what's work? Work is force times distance. Okay. And this is 1/2 mv final squared minus 1/2 mv initial squared. So you might get thrown because they use the word average. You'll see this a lot in problems. This is just basically a way for them to cover their bases while they're writing the problem, because the truth is that the force on the bullet is a highly variable thing. It's probably a lot at first and less as time goes on, but they're saying pretend that it was the same force the whole time, and that's the sense in which they mean average. Okay, so we know the bullet's initial velocity, and its final velocity is 0 because it ends at rest. So really what we have here is the average force times the distance it moves, which they tell us is 0.055 meters. Always convert to kilograms, meters, and seconds. This equals 1/2. So you may say, wait a minute, put the minus sign in. Okay, so I'll put a minus sign here, but now let's just think about this for a moment, and this is worth discussing. The bullet is moving this way. The superhero must exert a force in this direction. And to be more specific, work is F dot D, assuming it's a constant force. And so this is FD cosine theta. And the angle between these two is 180 degrees. So there's actually a minus on both sides. So I'll put it in and then we'll ignore it after that. But sometimes you'll see people just omit that. But the truth is we're doing the same thing every time. It's not a special technique for this problem. There really are minus signs on both sides. Okay. And then 1/2. And so MV initial. So the mass is 0.0078. And the initial speed was 575 squared. I'll pause while I calculate that. Okay, so you punch it into the calculator and you get this, and if you keep 3 sig figs, which is what everything else there has, you get that. Okay, the next part says, assuming the force is constant, determine how much time elapses between the moment the bullet strikes. Well, so here, if the force is constant, then F equals ma, the acceleration's constant, and we can just say, well, a is delta v over delta t, right? But what is A? A is force over mass. And so they want the time. We can just say delta t equals m delta v divided by the force. And if we punch all that in, we get something like 0.0019 seconds. Okay, so we'll call this one solved. Okay, so now we'll take a look at the second problem. This one is not so much work energy, but this deals with the other thing that they talk a lot about in this chapter, which is spring forces. And spring forces are funny because they depend on the distance. They are variable forces. Okay, so here it's a familiar setting. We've got a puck moving in a circle, okay? And we know that for a puck to move in a circle, it has to have a centripetal acceleration, v squared over r. Only this time, instead of having the puck attached to a rope or something with a tension T, it's got this weird variable spring force attached to it. And at first you might think, oh my God, this is going to be a nightmare. It's actually not so bad, but it is instructive to do the problem. It illustrates a lot of different things. So we'll take a look. This is the radius. This is the radius, but you might also think this is the distance x, but it's actually not the distance x. They say the spring has an unstretched length. Here's my spring. Let me coil it. That's my spring. They say that this is 15.5 centimeters. If I then make the spring longer by some distance delta x, okay, that's the x that we're talking about up here. So this r is the original spring length plus whatever I've added to it. So I've stretched it some too. So this becomes 0.155 plus x, however far I've stretched it. Okay, so we can come back down here and we can say, here's my free body, by the way. I've got centripetal force this way, which is kx, and then there's always weight down and there's normal up, but here like we're on a no friction horizontal surface, so all we'll get from this is that the normal equals mg, so I'm going to just ignore that direction. I'm going to look at the sum of the forces in the centripetal direction, which is kx, and that's equal to mv squared over, instead of writing r, I can write 0.155 plus x. Okay, at this point, it's mainly just algebra. There is one other little hiccup in this problem, and it's something you'll see from time to time. They don't give us the velocity, they give us the period, which is a little annoying. But think about what velocity is. Velocity is distance over time, right? Well, the time they're talking about is the period, how long it takes to go all the way around a circle. So the distance is 2 pi r, 2 pi r over the period. Okay, and so anywhere I see a v, I can put that in instead, and anywhere I see an r, I can put that in instead. So let me punch that. So that looks something like this. And then I've got the period, so I've got a number for that. And then what I really need to do, what the problem's asking for, is find the extension of the spring x as it depends on m. Okay, so I have two variables that I don't know here. I don't know x, k is known, and I don't know m. And then I'll punch in a bunch of numbers. I'll do some algebra. I'll pause. Okay, so we do some algebra, we punch some numbers into a calculator, and we get this. So this is really interesting and weird if you look at it, and they ask you to punch in a bunch of different m values, which I don't feel like doing. I'm more interested in just looking generally at it and saying, how does this depend on m? And if you look at this, it's really strange. The first thing that pops out to me is that the denominator can be a negative number depending upon the value of m. That seems very strange. They're saying that the denominator they're saying that the x, the amount the spring stretches, can be negative. That's crazy. That means the spring compresses. And we know that the spring has to stretch in order for this thing to be pulled inward. But if you think about this, in order for this to become negative, at a certain point it has to hit zero. If the denominator of a fraction is zero, it means that an infinite amount of force is required. This is fascinating, this problem. What it actually says is you can't put any mass you want and have this work given the value of this spring. So notice the 4.3 here, that's the k. So the bigger that number is, apparently the more mass we can use. But let's just see what happens if I let the denominator equal 0. So if the denominator is 0, 4.3 minus 23.4 m equals 0, then the force would be infinite. This actually puts a limit on the mass that I can actually do this with. So this is 4.3 over 23.4, and that's kilograms. If I have a mass that's larger than this, I get a negative number, and basically what the problem's telling me is it's impossible. You can't do it. This is the biggest mass you can have. And notice that in the top, it's the spring constant. So the tougher the springier the spring, the more mass you can have, right? But no matter what the mass is, you will at some point hit some limit. Other interesting things to think about are the spring. Let's say that the speed is fixed. Once the speed is fixed, right, you have some period. Now they give us the period. The spring, you know, is exerting a force inward the whole time. And you may say, well, how much work does the spring do as it goes around? Well, work is the spring force dotted with the displacement. So I'm actually going to write this. I'm actually going to write it differently. I'm going to say the displacement delta D, only because by x we mean how far the spring stretches. But when we talk about work, we talk about the distance the thing goes. And the distance it's going is in the circumferential direction. It's going circularly. The force points toward the center all the time. That actually means that the spring does no work once it has been expanded. Once it's been stretched, the spring doesn't do any more work. The spring does do work as it stretches, though, and we know, because we've calculated this before, that the work that a spring does is 1/2 kx squared. So I just wanted to point that out, that, you know, this nice feature of circles, or like if you have a guy on a rope and he's swinging, right? The tension or the spring force, we actually don't need to worry about the work anymore because it's perpendicular to the direction of motion. If I wanted to be a crazy maniac and make your life miserable, I could give you a problem on an exam where a guy is holding a spring at the top, like this Indiana Jones problem we did, and then he jumps. And as he jumps, the spring stretches, and he speeds up. I am not a crazy man. I'm not that much of a maniac. I will not give you that problem, but I bring it up because you may wish to think about it. Okay, that's it for this problem. If you have questions on the homework, hit up the homework discussion boards. If you have questions about either of these, same thing, hit up the homework discussion boards.